Hello friends, I welcome you all on India's largest live e-learning educational platform, that is Gradeup. Friends, today we are going to discuss some of the remaining portion of this series, startup series, that is dedicated for your subject electrical machines for electrical engineering students, and then we will be quickly starting the auto transformer also if the time permits. Now all of you who are joining the session right now, please tell me whether my audio and visual quality is okay for you so that we can proceed for the session. All of you who are joining me, quickly tell me whether my audio and visual quality is okay for you so that we can proceed for the session. Till then, one of you reports that audio and visual quality is okay. Let me just list out the topics that we are going to cover today. Very shortly, I will be going through. So the list of the topics that we are going to cover today. So we will be seeing starting from the practical transformer. Saran Kumar, Sanjay Bontu, please tell me whether my audio and visual quality is okay. So, students are reporting that it is okay. So, now let us proceed. So, today we are going to see the following topics, list of the topics we are going to cover. Number one, practical transformer. Okay. MMF balance, equation of a practical transformer, equivalent circuit. So many things we have to cover. Voltage regulation, efficiency, and then if the time permits, then we are going to see the auto transformer. And you should not be worrying about this because definitely we are going to take up each and every topic in detail. So time is not that limited for us right now. We are having plenty of time. The only thing is be we should be covering everything in a justifiable manner so that you understand things. Okay, friends. Now, before I start the session, I must tell you that all of you, please make it a habit that whenever you come for the session, don't forget to like this page and share this video among your friend circle, colleagues, groups, because it is very important that you keep on giving your response through these methods. Then only we'll be able to continue these sessions. Okay, now let us focus on the first screen, which shows how to wash your hands so as to protect yourself and others against the infections related to the novel coronavirus. This we are communicating under the initiative hashtag Prep Smart Stay Safe as started by Team Gradeup. So these are the steps how you should wash your hands properly. You should wash your hands under the direct tap water, apply soap, rub hands palm to palm, lather the backs of your hands, scrub between your fingers, rub the backs of the fingers on the opposing palms, clean your thumbs, fingernail, fingertips, then wash your hands under the direct tap water, dry it using a towel and switch off the tap by using a tissue paper, and now your hands are clean. And this whole procedure should approximately take somewhere around 20 seconds as per the government regulations. The next slide on your screen shows the contact number for the control room which is being set up at the national level to address the queries related to the novel coronavirus. You may reach this number for any guidance, support and technical queries. This also we are communicating under the initiative started by Team Gradeup as hashtag Prep Smart Stay Safe. I hope it is clear to all of you. Now there is one more information about the Gradeup free classes being offered in this time when everybody is restricted to stay in their home. M.N. Ramesh Sir, Chandan Sir, Rakesh Chaleja Sir, they are taking engineering services mains practice classes 9 a.m. in the morning. Chandan Jha Sir is taking concept on fingertips classes at 12 p.m. I am taking engineering ethics classes for engineering services paper 1 2021. Vijay Bansal Sir is taking concept on fingertips classes at 2 p.m. and M.N. Ramesh Sir is taking concept on fingertips classes at 7 p.m. I hope it is clear to all of you. Now there is one information regarding this Target Gate 2021 and electrical engineering course. The most important feature of this course is that it is going to be a bilingual course. It means इसमें हिंदी और इंग्लिश दोनों में बातचीत होगी so that language is no more a barrier for your learning. Rakesh Talreja Sir, MEIC Bangalore, AIR 9, 10 plus years of experience. Myself Ashutosh Saxena, M.Tech, IIT B.H.U, 10 plus years of experience. M.N. Ramesh Sir, M.E. Osmania University, Hyderabad, 17 plus years of experience. Vijay Bansal Sir, 19 plus years of experience. Chandan Jha Sir, M.Tech NIT Hamirpur, 9 plus years of experience. Thousands of students have started the free trial. At least all of you should go to the Gradeup app and should start the free trial to understand and to experience the way Gradeup is changing the life of thousands of its students. Good evening, Gonda. How are you? So now let us start with this. GB Raju, all of you, now just focus here. Now suppose this is your practical transformer, something like this. This is switch S1 at the source side or the primary side. This is your AC source, and suppose this is your load connected at the secondary side, and this is switch S2. Okay. Now the moment you close this switch, suppose at t is equal to 0, there is going to be some current I1 in this primary winding, yes or no? This we have discussed yesterday, and the current sense in the primary winding is going to be something like this. This is going to be the voltage applied by this supply voltage that we are calling as V1, and because of Faraday's law we have seen that there is going to be induced EMF is going to be E1, and it is going to be having the same polarity. If this is positive, then this is positive. If this is positive, then this is positive. Polarity also we have seen. Now suppose this switch is also closed. We have seen the transformer action also. So suppose the current direction is something like this. This switch is also closed. So the current is going to be in this direction. Okay. And there is going to be some EMF induced that we are calling as E2. And the terminal voltage across the load, this is your load, this we are calling as V2. This is the normal thing that we have discussed yesterday. Now because of the current in the primary winding, there is going to be some flux also there. I hope you are comfortable with this. Yes or no? Now if it is a practical transformer, what is the idea about a practical transformer? Practical transformer means that exciting current or magnetizing current is required to set up the flux in the core. When we were discussing the ideal transformer, we have discussed that for an ideal transformer, the permeability is infinite, we are assuming. So there is no exciting or magnetizing current required to set up the flux in the core. But in case of practical transformer, you do require some exciting current. So this is the first part. What is the second part? There is going to be the resistances in the primary and secondary winding. Suppose we are calling it as, suppose this is N1, this is N2. Suppose for this coil, primary coil, we are calling it as R1. Suppose here it is R1, okay, and here it is R2 for this coil, and there is going to be some leakage flux in the primary and secondary winding. You must be remembering how we have defined the leakage flux. Leakage flux is that flux which is linked only to one winding. Suppose if you talk about the leakage flux in the primary winding, then leakage flux at the primary winding is that flux which is linked only to the primary winding, not to the secondary winding. Similarly, if you see the leakage flux at the secondary winding, it is the flux which is linked with only secondary winding, not the primary winding. This is how we are defining the leakage flux. Now, in order to model this leakage flux, because you want to do the calculations, we represent this leakage flux in the primary and secondary winding by X1 and X2, which is the equivalent voltage drop, you can say. So here it is going to be X1 and here it is going to be X2. Now this is your practical transformer. But the idea is that what is going to be the MMF balance equation? What is going to be the MMF balance equation? Please try to understand. What is the total MMF? The total MMF is going to be how much? N1, I1. And this MMF is going to provide what? It is going to provide the compensation of the current in the load side or the secondary winding, that is N2, I2 plus N1, I0. Because this MMF is going to be divided into two parts. It is going to provide the magnetization of the core, because it is not an ideal transformer, it is a practical transformer, so some exciting current is required definitely. There is going to be losses also, and the secondary winding load side current I2 is going to give rise to an MMF N2 I2, and this is going to be compensated by the extra current drawn at the primary side. I hope you are comfortable with this. I hope you are comfortable with this. So you can very easily write that I1 is going to be how much? It is going to be N2 upon N1 I2 plus I0, or you can write I1 is equal to I2 upon N1 upon N2 plus I0, and this N1 upon N2 we are calling as transformation ratio, that is A. So primary current we can write as I2 upon A plus I0. This is the most important equation. I hope it is clear to all of you. Yes or no? I hope you are getting this. If you want, you can write this I2 upon A as I2 dash. What is I2 dash? You can write it like this also. You can write it like this also. I2 dash as I2 upon A, which is the current seen by the source due to connection of load at the secondary side. I hope you are getting this. Gonda Kavya is saying little bit confusing. What is your confusion, beta? Please tell me. Good evening, Ola. Please tell me, Gonda Kavya, what is your confusion so that we can discuss that. Please tell me what is your confusion so that we can discuss that. And all of you who are live with me in this session, don't forget to like this page. Repeatedly I am saying this. Don't forget to like this page. Okay. Ranjit Mahal is saying, sir, please repeat it. Okay. Now see how we are doing the MMF balance equation. How we are balancing the MMF. This MMF balance we have carried from the principle of or the concept of transformer action. What is transformer action? Transformer action is that if you close the switch at the load side, there is going to be some current in the load circuit or the secondary winding, and because of the current in the secondary winding, there is going to be some flux, some MMF, which is going to oppose the flux in the core. Yes or no? But the flux is not going to change because flux is going to be decided by the supply voltage. Supply voltage is not changed. It is a source. Its voltage cannot be changed until and unless you intentionally do it. So what is going to happen? At the primary side, some extra current is going to be drawn. And how much is this current? This current is going to be used to compensate the MMF of the secondary winding. That is what we are calling as the MMF balance or the transformer action. I hope it is clear to all of you. Now we are writing the MMF balance. This is the total current I1 multiplied by the number of turns at the primary side. So N1 I1 is going to be the total MMF at the primary winding. Now this MMF is going to provide the magnetization to the core. So this is N1 I0 and it is going to compensate. Compensate what? The MMF due to the current in the secondary winding because of connecting the load. So this is much. I hope you are getting this. So from here you can write I1 as I2 upon this. So you can write this equation. I hope that it must be clear to you, all of you. प्रिंस इज सेइंग सर एसएससी जेई क्लास क्यों नहीं ले रहे हो? बेटा जब सब्जेक्ट आएगा तभी तो लूंगा बेटा, सारे सब्जेक्ट मैं नहीं पढ़ा सकता ना। जिस जिस कंसर्न फैकल्टी का आएगा उसको वो लेगा उसको। अब मेरा अगर दोबारा से एसएससी जेई में आता है तो फिर से मैं लूंगा। आई होप इट इज क्लियर प्रिंस बेटा। आर यू कंफर्टेबल विद दिस? आर यू गेटिंग दिस आइडिया और नॉट? प्लीज टेल मी। नाउ लेट अस ड्रॉ द phasor diagram and you should be very cautious to understand this. First of all, this is going to be the flux. Okay, this is going to be the flux. So we are saying that this is the flux in the core phi. Okay, and there is going to be some current which is required for magnetization that I am writing as I mu. Okay, and the core loss component we are writing as IC, and this IC and I mu, they are going to give you the no load current I0. This is your I0. This is the magnetizing component of the no load current. What is I mu? I mu I am writing as the magnetizing component of the no load current. Yes. What is IC? IC is the core loss component of the no load current. I hope you are getting this. Mahendra beta, you are asking about humming sound coming from the transformer. We are still in the designing part of the transformer. Once we will be having the complete analysis of the transformer. Whenever transformer is designed, then only it is going to operate and then only humming noise is going to come. Right now we are at the designing stage of the transformer, you can say like that. So our transformer is right now producing no noise. It is calm, composed. Now focus here. Now this I0 no load component of the current, just go back and see what is the equation. This is added with this component I2 dash. Where is going to be I2? Just tell me. Where is going to be I2? Suppose your I2 is somewhere here. Suppose your I2 is somewhere here. This is your I2. Okay. if this is your I2 and you are saying I2 dash is I2 upon A, where A is N1 upon N2, and for a step up transformer, step down transformer, let us talk about a step down transformer. For a step down transformer, N1 is going to be more than N2. So A is going to be more than 1. So you can say if this is I2, so where is going to be I2 dash? I2 dash is going to be somewhere here. I2 dash is going to be I2 upon A. I hope you are getting this. Now if this is your I2 dash, what is going to be I1? How you are going to write the I1? The phasor sum of I2 dash, and I naught, that is the no load component, Sai Kumar is saying that there are some mistakes in the schedule. Beta, it is not mistake in the schedule because of some technical issues, because some of the 1 or 2 classes that were cancelled because of some technical issues, and we all are working from our home. So that is why we are little bit lagging from the schedule. I hope it is clear to all of you. Sai Kumar, just have little patience. What we are discussing is more important than your concern about the schedule. I hope within this week we will be able to pace up with the schedule. Just 2-3 days we need, because if we want to cover it very quickly we can cover it, but it will not be justified. So just listen to me properly. Don't worry about the schedule. We will quickly catch up. Now the phasor sum of this no load component and this I2 dash current is going to give you what? It is going to give you the I1 current. I hope you are getting it. Okay. So what is going to be your I1? I1 is going to be something like this. This is going to be your I1. I hope it is clear to all of you. So is it clear? And suppose this is E1. Suppose this is E1. So this is how different currents in the transformer for a practical transformer are looking like. Now let us see how we are going to model the leakage flux. Okay, now let us see how we are going to model the leakage flux. Now you see, at the primary side, suppose this is phi L1. What is phi L1? Leakage flux at the primary side. Similarly, we are going to write in the direction of I2 the leakage flux at the secondary side, that is phi L2. Now we are going to model these fluxes in terms of reactances. In terms of this phi L2 is going to be leakage flux at the secondary side. I hope it is clear. Now what we are going to do, we are going to represent this leakage flux as EL1, and we are going to represent this leakage flux as EL2 in terms of voltage drop. I hope it is clear. So what is going to be EL1 and EL2? Just focus here. EL1 beta is going to be how much? EL1 is going to be JI1X1, and what is going to be EL2? JI2X2. So it is going to be 90. EL1 is going to be 90 degree to I1. EL1 is going to be the 90 degree to I1, something like this. Please try to understand. And EL2 is going to be 90 degree to I2. So it is going to be something like this. So this is your E1, this is your E2, and this is the understanding how we are going to model the X1 and X2 in the circuit. All of you, please tell me, till now, are you comfortable with this? Please tell me, till now, are you comfortable with this? Whatever we have discussed, that is important. Please tell me whether you are comfortable with this or not so that we can proceed. Quickly tell me. All of you, please tell me, are you comfortable with this? At least tell me yes or no so that I can proceed. It is the only way I can get your response. Okay. Now let us see how we are going to write the MMF balance for a transformer. We have seen it for a two winding transformer. Now I am going to give you, suppose a three winding transformer when a tertiary winding is also there. Suppose the situation is something like that. Suppose the situation is something like this. Suppose this is the primary winding and this is the load side, this is the secondary winding and this is the tertiary winding and this is the primary winding. I hope it is clear to all of you. Suppose this is the AC source connected at the supply side. Suppose here the current is I1 and suppose some load is connected here and the switch is closed at the secondary and tertiary winding, so that suppose there is going to be some current I2 and there is going to be some current I3. Suppose there are N1 number of turns, there is N2 number of turns and there is N3 number of turns. I hope it is clear to all of you. Now if you want to write the MMF balance equation, always remember the way I told you for a two winding transformer. How it is going to be? First of all, you have to write N1 I1. This is the total MMF at the primary side. So what it is going to provide? It is going to provide the N1 I0, that is the magnetization of the core, plus the MMF balancing or compensation of the secondary and tertiary winding. So this is going to be how much? N2 I2 plus N3 I3. This is we are calling as the MMF balance equation for a transformer. If you understand this, if you can write it for a two winding transformer and a three winding transformer, then you can write it for any transformer, and it is going to be very important in solving numericals when it comes to GATE and engineering services examination. Now we are going to proceed some mathematical interpretation so that you can understand the whole idea. Now suppose I am going to write I1 as something like this, N2 upon N1, this is I2 plus N3 upon N1 I3 plus I0. Is it clear? Now I am going to take the conjugate on both the sides, taking conjugate on both the sides, taking complex conjugate on both sides. What you are going to get? I1 complex conjugate is going to be N2 upon N1. This is going to be I2 complex conjugate plus N3 upon N1. This is going to be I3 complex conjugate plus this is going to be I0 complex conjugate. Is it clear? I hope you all are following whatever we are trying to discuss. Now I am going to multiply this equation with V1 on both the sides. multiply V1 on both sides. So what you are going to get, please tell me. You are going to get V1 I1 complex conjugate is equal to V1 N2 upon N1, and this is I2 complex conjugate plus V1 N3 upon N1, and this is going to be Ranjit, beta, when it is a three winding transformer, beta, when it is three winding transformer, then you have to see the transformation ratio for this separately and transformation ratio for this separately. For this, transformation ratio is going to be between primary and secondary winding as N1 is to N2, and here it is going to be N1 is to N3. I hope it is clear. Yes, Yaram Mahendra, if you change the load, definitely the power factor is going to change. That we will see when we will see the phasor diagram. Don't worry. Okay. Okay. Now, why I am taking the complex conjugate, you will understand in a time. Please wait for the moment and you will understand this. Plus, this is going to be V1 I naught complex conjugate. Now, you tell me, what is this V1 I1 complex conjugate? You remember something? This is going to be the power at the primary side. How we define the power in polar form? Voltage multiplied by current complex conjugate. I hope you should be having this understanding why we take the complex conjugate of the current, not the voltage. All these things, I think you should be having the understanding. What is this V1 multiplied by N2 upon N1? This is going to be V2 and this is going to be V3. So what is V2 I2 complex conjugate? This is going to be S2 plus this is going to be S3 plus S0. So this is how it justifies this MMF balance leads to your power equation also, you can say. Is it clear to everyone? All of you, please tell me, are you comfortable with this? Are you comfortable with this understanding or not? Please tell me. I hope you are comfortable with this. Now let us proceed. I hope you are comfortable with this. Please tell me quickly so that we can proceed further. Are you getting this? Now let us proceed for the equivalent circuit. Now if you see in general how your transformer looks like, suppose this is your transformer. Suppose this is your transformer. Okay, this is V1, this is I1. Okay, this is V2, this is I2. There is going to be induced EMF E1 and there is going to be induced EMF E2. Yes or no? Now for this transformer we are going to draw the equivalent circuit. How we are going to draw it? Please try to understand. You all of you must be knowing this. Okay. So this is the primary side. This is the primary side Let us see the secondary side. Secondary side we are writing like this. This is the secondary side. Now this is going to be your voltage V1, this is R1, this is X1, this is R naught you can say, and this is XC. This is R2, this is X2, this is going to be your terminal voltage at the load side, this is going to be your induced EMF E2 at the secondary side, and this is going to be your induced EMF at the primary side E1. Now this is your ideal transformer, isn't it? Now this is your ideal transformer like your previous case that we have just discussed, and suppose this ratio of turns, number of turns ratio is N1 is to N2. Ranjit Mahal, beta, what to repeat? Every time you say repeat, what do you want me to repeat? Please tell me. I am going very slow. You exactly tell me what should I repeat. What is your doubt? If every time you ask me to completely repeat the concept, it is not that possible. You can pinpoint, sir, this is something we did not get. Please repeat it. Then I can repeat it. If simply you keep on saying, sir, repeat, 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 so it is going to be very difficult, beta. I hope you understand this. Now please try to understand. This R1, R2, they represents copper losses in the primary and secondary windings. X1, X2 represents the leakage flux in the primary and secondary winding. R naught represents the core losses that we will see when we will discuss efficiency. What are core losses? And XC is the representing the magnetization. I hope it is clear to all of you. Now for this secondary side, I am going to write the KVL equation. For the secondary side, I am going to write the KVL equation. See how I am going to write it. It is going to be how? It is going to be E2 is equal to V2 plus I2 R2 plus I2 JX2. This is simple KVL equation. All of you should be able to write this. I am simply writing the KVL equation. Here the current is I2. Here the current is I1. And here the current is I0. I hope it is clear to all of you. Can you tell me what is the current here? It is going to be I2 upon A. You remember that MMF balance for the practical transformer? Yes or no? Now if you are writing the KVL equation for this circuit, so you are going to get this equation. E2 is equal to this much. Now I am going to apply this E1 upon E2 is equal to N1 upon N2 or A, that is the transformation ratio. Yes or no? It means E1 is going to be A times E2. Are you getting this? Suppose we are calling this as E2 dash. This is very important and you should understand this, because then only you will understand how we are going to refer the secondary to the primary side or the primary to the secondary side. So what I am going to do, I am going to multiply this equation. I am going to multiply this equation by A. Suppose this is equation number 1 and I am going to multiply this equation 1 with A. So it is going to be A E2 is equal to A V2 plus, you can say it is going to be I2 A R2 plus it is going to be I2 J X2 A2, you can, sorry, not A2, it is A. Just write it AX2. Okay. Now what is this? A times E2 dash, this is going to be A times E2, it is going to be E2 dash. What is A times V2? This we are calling as V2 dash. And suppose you divide here by A and multiply it by A, so this is going to be A square. Similarly, you divide by A, multiplied by A, so this is going to be A square. And you remember this we were calling as I2 dash. So your KVL equation is going to be V2 dash plus I2 dash. This is A square R2 plus J A square X2. This you can simplify as E2 dash is equal to V2 dash plus I2 dash, and we are taking the A square common. So this is going to be R2 plus JX2, which you can write as Z2. I hope you are getting this. Now you will understand why we square the turns ratio like this when we refer the secondary circuit to the primary circuit. Now when we are having this equivalent circuit, it is very difficult to apply the KCL and KVL equations, because this is just a simple transformer, and if you see your actual power system, then you are going to have n number of transformers. So we want some equivalent circuit which is very easy and comfortable to do the calculations. So what we are going to do, we are going to remove this discontinuity, and if you want to remove this discontinuity, then what you have to do, you have to refer this. Suppose we are going to refer this circuit to the primary side. Suppose we are going to refer this circuit to the primary side. So it means everything you take at the secondary side and just go to the primary side. So what is going to happen? I2 is going to become I2 dash, V2 is going to become V2 dash, E2 is going to become E2 dash, R2 and X2 are going to become R2 dash and X2 dash. I hope it is clear to all of you. So from this equation beta you can write, draw this equation, and this is going to be the equivalent circuit that we wanted to generate. Suppose this is the load connected, this is the shunt magnetizing branch, okay. Now this is your V1. Now the moment you remove the discontinuity, this is going to be R1, this is going to be X1, this is going to be the R0, and this is going to be XC. Here it is going to be current I0, and here it is going to be I mu. Not, it is not I0, it is going to be IC. It is going to be IC. This current is going to be I0. This is going to be R2 dash, X2 dash. This terminal voltage is going to be V2 dash. This voltage we are calling as E2 dash, and this voltage we are calling as E1. This current we are calling as I1, and this current we are calling as I2 dash. And this is your load, and obviously if you are referring the secondary side to the primary side, it means you are also referring the load also. So suppose this load is ZL, so you have to use ZL dash. Now what is ZL dash? That is very important, and we call it as Z2 dash also. Now what is Z2 dash and ZL dash? Please try to understand. Z2 dash is going to be Z2. Now I am going to tell you a logic, the logic that I used to use when I do the calculations, and I think it is going to be easy for you also if you remember this technique. Okay, suppose you are referring secondary side to the primary side. So your source, what is your source? What you are referring? You are referring the secondary side. So secondary is your source. So from where you are referring, you keep it below the number of tons. So it is going to be N2. And from where secondary you are going to primary. Primary is your destination. Source is secondary here and destination is primary, because you are going from secondary to primary. So destination you write in the numerator and source in the denominator and just square it. This is how you are going to, you will never do a mistake in this if you follow this. Suppose you are going from primary to secondary. Suppose it is Z1. How you are going to change this in Z1 dash? कहां से जा रहे हैं? From where you are going? N1. Where you are going? N2. Just square this. This is going to be Z1 dash when you refer it to the secondary winding. I hope it is clear to all of you. Similarly, if you want to refer the load impedance ZL, so ZL dash beta is going to be how much? This is ZL. From where you are going? N2. Where you are going? N1. Just take the square. So all of you please tell me, are you comfortable with this understanding of the equivalent circuit of the transformer? All of you please tell me yes or no whether you are comfortable with this understanding of the transformer or not. All of you please tell me quickly, are you comfortable with this understanding or not? Better please quickly tell me, because we have limited time and we have to do a lot of things. Okay. Now see, we are having some approximate equivalent circuit. The first approximate equivalent circuit. Okay, Bhanu Pratap is comfortable. What about other candidates? See, all of you, don't forget to respond. If you don't respond, how I'm going to get that whether you are getting my point or not? It is very important that you keep on responding. Let us make it more interactive. And I want more and more of you. Bhanu Pratap is asking, sir, are you residing in Ghaziabad? Yes, beta. Are you coming? Should I wait for you, Bhanu Pratap? Are you coming to Ghaziabad? Yes, I do live in Ghaziabad, beta, but my hometown is Lucknow. Okay. Now just see here the first approximate equivalent circuit. The first approximate equivalent circuit is beta going to be something like this. Now you will say, sir, you have just shifted the, now some of the candidates will say, okay, great Bhanu Pratap, so you are my neighbor, thank you so much. You just contact me, definitely we'll meet, okay? Now just let us focus on the lecture, because we are living in Crossing Republic, Ghaziabad, but others are not living here. So let us others also enjoy. We'll talk later, Bhanu, okay? Whenever you want, you come to me, definitely we'll meet. Okay? Now just see here. First approximate equivalent circuit we want to see, but some of you will say, sir, you have just shifted the shunt magnetizing branch. What is that great in this transformation? Now if you see beta, what I have done, can you see what is this? This is R1, this is X1, this is R2, this is X2, obviously dash dash, and this is R0 and this is XC. If you see closely, this R0 represents the core losses. This R0 represents the core losses. And this R1 and R2 represents the copper losses. So if you are using this equivalent circuit beta, so what is happening? This circuit we are going to use when we are going to calculate the efficiency, because you have separated the core losses and the copper losses, and this is a very beautiful thing because your calculations are going to be very easy. Now suppose this is I1, this is I0, this is I2 dash, this is V2 dash, and this is going to be your V1 dash. All these things you can correlate. Okay. So this is for efficiency calculation. When nothing is mentioned, this is going to give you very accurate result because the transformer efficiency is going to be very high, almost more than 90%, because it is a static machine. So if you take this approximation, even though your efficiency value is going to be very close to the actual value, so for all the efficiency calculation, if nothing is mentioned, you can very easily go for this approximate equivalent circuit. This is the beauty of this approximation, that core losses and copper losses are being separated. That is very important. Now let us go to the second approximation. Let us see the second approximate circuit. How we are going to see the second approximate circuit? Just see here. For the second approximate circuit, the shunt magnetizing branch is neglected. Now see what is going to happen. So your transformer is going to look something like this. Very beautiful transformer you are going to get. This we are calling as R1 equivalent, and this we are calling as X1 equivalent. This we are calling as V1, and this we are calling as V2 dash, and this is your current I1, or better to write it I2 dash. Same thing, no change. I1 is going to be equal to I2 dash because of the approximation. Suppose this is I1 and this is we are writing as I2 dash. So I1 is equal to I2 dash if you take this approximation. You have neglected the magnetizing shunt branch, and you must be knowing what is this Z1 equivalent and X1 equivalent. This R1 equivalent is nothing but R1 plus R2. Now whom you have shifted? R2. From where? Secondary to where? Primary. Take the square. X1 equivalent. So it is going to be X1. Whom you have shifted? X2. From where? N2. To where? N1. Take the square. Now this equivalent circuit is going to be very helpful when you are going to calculate the voltage regulation. Now can you tell me this equivalent circuit of the transformer, it resembles what? It is very simple RL series circuit, like your short transmission line when you read the power system. So whenever you are going to calculate the voltage regulation, this approximate equivalent circuit you can use, and it is going to give you very accurate, almost accurate results, I can tell you. If nothing is mentioned, if everything is clearly given in the problem, suppose it is an engineering services mains conventional problem, then you cannot ignore it. Then you have to take into account everything, and you have to do the detailed analysis. So this is, we are going to, this equivalent circuit we are going to use when we are going to discuss the voltage regulation. All of you, please tell me, are you comfortable with this? Are you comfortable with this? Can we proceed? Tell me yes or no. Are you comfortable with this? Please tell me quickly. Please tell me, are you getting what I'm trying to say? Okay. Now let us see what is voltage regulation. Now before I tell you what is voltage regulation, it is very important that you have a general understanding of why we are so much worried about voltage regulation. Now the moment you have designed your transformer, what is the purpose of transformer, you tell me? Why you have designed the transformer? Because you want to step up or step down the voltage. That is the primary criteria, primary requirement of a transformer. There are other applications also, but we are going with the prime consideration. The prime application of a transformer is step up or step down the voltage. Now suppose you have sold your transformer to the ultimate consumer and you have told him that if you apply V1 voltage at the primary side, then you will get the V2 voltage at the secondary side. Are you getting this? See, the situation is something like this. This is the primary, this is the secondary. The consumer is going to apply the voltage V1 at the primary side, suppose, and he is going to get the voltage V2 at the secondary side. That is what you told him. Are you getting this point or not? But suppose instead of getting this voltage V2, actually he is getting some voltage less than this voltage V2. This is the reality. Are you getting this? Because your transformer is not ideal. Your transformer is a practical transformer. You told him that you apply V1, you are going to get V2. But in reality, you will get a little less than V2. Why? Because of the different load conditions. You don't know how much load your consumer is going to apply. So what you are going to do, you will perform the test in terms of voltage regulation criteria. You will check what is voltage regulation of the transformer, and when you will sell the transformer to the consumer, you will say this is the voltage regulation. So what is the meaning of voltage regulation? Voltage regulation is going to give you the worst case voltage drop at the secondary terminal. Let me put it in the very short and direct statement. Voltage regulation is going to give you the worst case for a given load, the worst case voltage drop at the secondary terminal. So that if your consumer is not getting that required voltage, that he is not going to complain and he is not going to give that transformer back to you. I hope you are getting this idea. Now suppose you are having the equivalent circuit that we have just derived like this. Suppose this is the equivalent circuit that we have just derived to calculate the voltage regulation. Suppose this is the input voltage, we are saying this is input voltage V in, and this we are defining as the secondary load terminal voltage V2, or simply V you write it, okay. And suppose this is going to be Z1 equivalent, and suppose the current is going to be I here. All of the approximation we have taken. So what is going to be the voltage regulation? The voltage regulation is going to be V in minus V upon V multiplied by 100%. So this is how we are going to define the voltage regulation. If you want to write the definition, then you can write it that voltage regulation of the transformer is defined as the rise in output voltage as a fraction of input voltage when the load is reduced from full load to zero at a specified power factor. I hope you are getting this. Yes, Gonda Kavya, you are perfectly right. I knew that this confusion is going to come, but you actually sorted it before student asked it. Some of you might have seen that in some of the standard textbook, if you go, then you will find the voltage regulation formula for the transformer as E2 minus V2 upon E2. And it is very confusing that somewhere you are using this formula, somewhere you are using the full load condition. What is the actual problem? The problem is, beta, that if nothing is mentioned, let me tell you, if nothing is mentioned and it is an objective problem directly, so you have to decide as per the data given in the problem. That is how you are going to decide it. Because there is one convention which says that you always calculate the voltage regulation with respect to the secondary rated voltage, that is this much E2. And there are some conventions which we say that we have to represent it in terms of full load. So it depends on convention, which convention you are following, and you have to decide as per the information given in the problem. Okay. Yes, Ranjit Mahal, it is your way, but you don't tell this thing in the interview. If you tell this type of things in the interview, then it is going to be very difficult interview. Let me tell you, this is going to be very difficult interview if you tell like this. Okay. So we are defining the voltage regulation like V in minus V upon V if you are writing in per unit, and this is going to be V in minus V minus 1 per unit. Now let us draw the phasor diagram for this equivalent circuit and see how we are going to get the approximate value of the voltage regulation. I hope you are ready for this. Now see how we are going to write it. Suppose we have taken V as the reference. Suppose this V is our reference. Suppose this V is our reference, okay? And suppose this is the lagging current. We have a lagging load. Suppose we are drawing it for a lagging load. So this is the lagging current. This is the voltage V. This is the lagging current I. And if you see this diagram, this is simple RL circuit. And this Z equivalent is nothing but R1 equivalent, and this is X1 equivalent. So this current I is the lagging current with respect to this voltage, and this is going to have two drops, resistive drop and reactive drop. The resistive drop is going to be in the direction of current. Yes or no? In the direction of current. So this is going to be how much? This is going to be something like this, parallel to I, because it is resistive drop. And you are going to add here the reactive drop at right angle like this. Yes or no? So this is going to be your how much? This is going to be IR, and this is going to be how much? This is going to be the IR equivalent, and this is going to be IX equivalent with J. So it is leading with 90 degree. Now what is the, suppose you want to write the input voltage. So your input voltage beta is going to be something like this. I hope you are getting this. Now just see very carefully. This we are defining as the power factor, lower power factor of the load connected at the secondary side, which is phi. Yes or no? And suppose this we are defining as del. For example, we are taking del. Now suppose I want to extend this V like this. Suppose we are extending this V like this. Okay. So this angle is also going to be how much? This is also going to be phi. Yes or no? Now if I draw a direct from V to V in. Yes or no? So this is going to be your V in and this is your V. So this value is going to be how much? This is going to be I Z equivalent. Yes or no? R equivalent, X equivalent. So this is going to be how much? Are you getting this or not? This is going to be the I Z equivalent. And can you tell me what is this total angle? This total angle is going to be theta equivalent. Yes or no? Because this is between R and Z, so this is going to be, just take this example. Suppose this is R equivalent, this is X equivalent, and this is going to be your Z equivalent. So this angle you define as theta equivalent. We can say the impedance angle of the transformer. So this impedance angle of the transformer is going to be between R equivalent and Z equivalent. So can you tell me what is going to be this angle? Can you tell me this angle? This angle, can you tell me? Yes. This angle is going to be theta equivalent minus phi. This is very, very important. Now if you see, suppose this is O, this is A, and if you take an arc, suppose it cuts this extended line here at B, and if you take the projection of this V in here, so this is going to be C. Now we are assuming for approximate value of the voltage regulation, we are saying for the approximate value of the voltage regulation, we are saying that this OB is approximately equal to OC. So can you tell me what is OC? OC is going to be, suppose this is D, this is going to be OD plus DC. Yes or no? This OC is going to be OD plus DC. What is OD? OD is V plus what is DC? DC is the projection of IZ equivalent with respect to this cos of this angle. So can I write like this? Yes or no? So this OC I am writing. OC is going to be how much? OC beta is going to be, OC is going to be OD plus DC. OD plus DC. What is OD? OD is going to be V. What is DC? This distance I am asking you, this distance DC. Can you tell me? Yes, this is the right angle triangle. So you can have IZ equivalent cos of this angle. So this is going to be IZ equivalent cos of theta equivalent minus phi. Now you tell me what is voltage regulation. Can you tell me what is voltage regulation? You remember the formula or not? So voltage regulation is going to be V in. What is V in? V in is OA. Yes or no? And OA and OB are going to be same because this is a curve with this radius V in. So V in is going to be OA or OB. So this is going to be OB minus V. What is V? V is going to be OD. You can write it as OD divided by OD. So what is OB? You tell me. OB is approximately OA is equal to OB is approximately equal to OC. So this is going to be OD is nothing but V. So this is going to be V plus IZ equivalent cos of theta equivalent minus phi. And this is going to be minus OD. What is OD? OD is V. And this is going to be divided by V. Now V is going to be cancelled. Now you keep this I below this V. Yes or no? So this is going to be what? This is going to be Z base. Yes or no? This is going to be Z base. This V by I. So you will get Z equivalent divided by Z base, where Z base is nothing but V upon I, and this is going to be cos of theta equivalent minus phi. So you are going to get the voltage regulation approximate formula as Z per unit cos of theta equivalent minus phi. I hope you all are comfortable with this. I hope you all are comfortable with this formula. Please tell me yes or no. Please tell me, beta, are you comfortable with this? Gonda Kavya, beta, what is your doubt? Friends, with this I am going to stop here because we have already moved beyond time, and I knew that we are lagging with respect to the schedule. As per, suppose we have to complete the auto transformer today, but don't worry, slowly we are going to pace up with the topic very quickly. So you don't worry about that, but the most important thing is that whatever we cover it with 100% honesty, so that you understand it and it is going to be helpful for your examination. I hope you all are comfortable. Whatever we have discussed, just go through this. Now I'm going to discuss some of the important points about this target batch and efficiency, and this auto transformer part we are going to discuss tomorrow with the tomorrow's topic. So these are the highlights of the Target Gate 2021 batch. 550 hours of live classes, 5,000 plus practice questions, study notes. Nobody gives you study notes. Full length mock test, daily tested subject wise test. These are the important dates, and this 11th May is the most important date because GST is going to be conducted on 11th of May. If you want, you can take the screenshot, beta. So the remaining part of efficiency and auto transformer along with the tomorrow's topic we are going to cover tomorrow. So don't worry about that. So tomorrow, beta, if the time permits, we are going to take up these three-phase transformer connections apart from it. Solution and specialist is saying, sir, gate 2022. बेटा अभी 2021 को फॉलो करो ना. Now this is very important. 60 plus students from the Gradeup, they have acquired the top 100 ranks, within top 100 ranks in the gate 2020 examination. If you want, then your name and photograph can be here, but you have to really work very hard. You have to put 100% of your efforts, 100% of the honesty if you want to see your photograph here, beta. So friends, thank you so much for your time. I wish you all the best for your upcoming exams. Don't forget to join me tomorrow 8:30 p.m. in the evening, and we are going to discuss a lot of interesting things tomorrow. Thank you so much for your time. I wish you all the best. Don't forget to tell me your feedback in the comment section so that if there is any lagging from my side, I can improve upon that in my next classes. Your suggestions for improvements are always most welcome. Yes, Gonda Kavya, in general, this is going to be the formula. See, let me tell you that this is the voltage regulation formula we normally use everywhere. So we have to take a, this is, you can say, a modern convention. That old convention E2 minus V2 upon E2, that is the old convention. So some of the textbooks, they are following that old convention. But the modern convention is to represent the voltage regulation in terms of full load. That is the idea. So all of you, don't forget to like this page and share this video if you want more and more such videos, because this week I hope that we will be able to cover the transformer part, and very quickly we are going to start the synchronous machines in this series also. That is going to be very helpful and very important for you to understand a lot of things. So don't forget to like this page, then only we can continue these type of sessions for you. And I wish you all the best, beta. Don't forget to join me tomorrow 8:30 p.m. We are going to discuss the efficiency part, the remaining part of the auto transformer we are going to discuss tomorrow, and we'll discuss the three-phase transformer connections also. Thank you so much for your time. I wish you all the best. Good night. Sleep healthy and stay safe in your home. Thank you so much.